Hey, Christina. How are you? It's good to see you.
I'm good. Good to see you too.
Good, that's good. We're gonna start like in literally 30 seconds. Just give me 1 minute. All right, good to go. Good to go. And good evening to everybody on YouTube. Oh, Christina, you're on YouTube too. Good evening, Z. Good evening, Jolene. We are gonna get started now. All right, so it's good to see you guys. Let's see what we can do with circuit theorem. Based on the poll I sent out, a lot of you guys wanted to look at circuit theorem, so that's why we're choosing this one for today. All right. So we're gonna kind of recap the theorems a little bit, and then of course go into some past paper questions. See? No. Before we start, I want you guys to rate yourself. Tell me, where would you put yourself with circuit theorems? As usual, on a scale of 1 to 10. Where you guys at? So I can at least know what pace we're gonna move at. Let's say there's a 1, a 10, 1,000. Okay, yeah, you like it? Yeah, that's pretty cool. That's nice. That's nice. Not a lot of people like it, so it's good to hear somebody say that they like it. That's good. And one of the reasons why we're doing this topic too is because it's one of those topics that it's very consistent in how it comes. And once you know the theorems, about 6 or 7 theorems, then you'll be able to do any problem that has them in it. So it's one that it's really important for you to know and know when to identify the theorems. All right, I'm seeing some 5.5, some 2s, and a 7 from V. All right, no problem. So if you didn't do it, I'm kind of just going to give you an overview of what is involved. Cool. Now, the circle theorem, as its name suggests, it's a group of theorems about circles. A theorem is kind of like, it's like a court case in a sense where, in a court case, you have to lay out and you have to prove and you have to use this evidence and that one to show that something happens. It's the same thing with circle theorems. You're using all of these theorems to prove things about circles. Now, these are basically the circle theorems that you need to know, that you definitely need to know. And well, I'd say this was the poster that I found, but excluding this one, let me use my thing here. So I don't really see this one much. So excluding this one, you definitely need to know these 7. And so these 7 you need to know. And the whole thing when it comes to circle theorems is knowing when to use what. So as we go in this session, we're just going to think about when do we use particular theorems for circles. So let's kind of recap each of them. Do you see any here that you are not familiar with? In other words, out of 7, because there are 7 theorems, which one of these theorems are you seeing for the first time? How many are you seeing for the first time? Like if it's 1, you put the 1 out of 7, 2, you put 2 out of 7. Or if you know all of them, then you put the 7 out of 7. They put the 0 out of 7, sorry. Have you seen all of these before? All right. Okay, good. Christina says 0. That's pretty good. Stacy said 1. Oh, that's good. Oh, you say you don't like circuit theorems. Yeah. We're going to work on that. So remember, while we're going along, if you have any questions at all, remember you can write it in the chat. If you have a lot to say or ask, then you can come onto the Zoom and ask it out loud. Of course, I'm here to help you. All right. So let's kind of recap each of them. So this one says that the angle at the center is twice the angle at the circumference. And you'll generally see it looking something like this, but it can be different. It doesn't always have to look like this. And what I'd add to this definition is that the angle subtended at the center, meaning the angle that's going in the same direction as the other, okay? So that's very, very important. It's kind of like it's pointing to it in a sense. So that is one theorem that you need to know. Another common one is angles in the same segment are equal. And sometimes people call this the bunny ears theorem. I heard that this week. Because if you're looking for it, you can kind of look at it like the ears of a rabbit. Like, look, you see it? Like if I could draw, I can't help myself, I'm not a pro, but it would kind of look something like that. I don't want to scare you. I'm not going to try to draw any rabbit. That good. But yeah, this is one that you'll see. I remember that for this one, essentially the key thing is that they start from the same place. So what it's basically saying is that once an angle starts and ends at the same place, or it's coming from the same place, then they're going to be the same. That's why you might also see they say angles in the same segment on the same chord are equal. This other one, the angle in a semicircle is 90 degrees. That's a common one as well. Opposite angles in a cyclic quadrilateral, that means all the corners of the quadrilateral touch the circle. The angle between a tangent and a radius is 90 degrees. You know that one as well. Where it's just saying that once you have a radius meeting a tangent at a point, it's going to form a 90-degree angle. Tangents from a point outside a circle are equal in length. In other words, this is known as the hat theorem, because you kind of see it looks like a hat. Yeah, something like that. So that's one. And then you have the alternate segment theorem. And now this one is the one that usually saves the day sometimes. But sometimes this one can show you something really easy right in front of your face instead of you having to go around in different places. And it's just basically saying that the angle formed between the tangent and the chord is equal to the angle in the alternate segment. So in other words, this angle down here, the angle formed between the tangent and the chord, it's going to be equal to the angle in the alternate segment. In other words, it's like the angle facing the one that you just found. So that's why that angle A would be equal to A up here. And likewise, the angle B right here would be equal to this angle up here, which is B. All right? So those are basically the theorems that you kind of want to know. You understand? And what you need to do whenever you're doing some CSEC problems, one of the best things that you can do is while you work, while you go through, it's like you keep a little snapshot of these in your mind. Because they're not on the formula sheet, you know, so you have to know them. So you have to treat them like things that something that you would just remember how to do. And when you're going there, you're going to basically be looking for these things, okay? So you're going to either be looking for some of the diagrams that look this way, look this way, or the shapes that look this way, and that will help you to do them. All right? And that's exactly what we are going to do today. Okay? So guess what? Let's start. Let's look at some CSEC questions. But one of the things that you have to remember too, what we're going to focus on as well is giving a reason for each of our answers. Because one of the problems in CSEC, why students lose marks here, is because they don't give the reason. So you have to give a reason. I'm going to make sure for each of the ones that we do, we give a reason. All right? So enough talking. Let's get started. Now, in this question, I don't remember what year this is. but oh, I'm seeing somebody in YouTube, somebody asking to Tamoya, asking to go over the second one. All right, let's go back. Second one, is it this one? Angles in, no, it says subtended angles. Oh, must be this one. So the angle at the center is twice the angle at the circumference. When I say subtended, it means the angle going in the same direction as that one, okay? As the angle at the circumference. So what it's saying is that it's 2 times that. It's twice that. So if this is A, then this would be 2A. So for example, if this angle was 50 degrees, then the angle at the center would be 100 degrees. Okay? If this angle was that don't look like 100 degrees, probably let's say it's 27 degrees, then the angle down here is going to be 2 times 27, which would be 54 degrees. So the angle at the center is twice the angle at the circumference. Okay. The second one, the angles in the same segment are equal. Yeah, what we're saying is that basically once they start and end at the same place, then the angles are going to be the same. So if you look at this one, right? This angle starts here and ends here. Let me put some names for the point. So let's call this point A, B, C, and D. So if you look at this angle here, ADB, we're saying that it's going to be the same as ACB. So those angles are going to be equal. And you can know that they're equal because they start and end at the same place. They both start at A and end at B. If I were to draw some other line here, let's say I drew this one, and let's say that this point was E, then AEB would also be equal to ACB and ADB because all of them are coming from A and end at B. I can go the other way around. It can start at B and end at A, but they just have to share the 2 common points. Once they do that and they're in the same segment, that is, a segment splits a circle into 2 parts, and this is the segment we're talking about. So once they're in the same segment, then they're going to be equal. All right. Yeah, I hope that helped. What I'm saying. Let me know. All right, boom. Let's go to the next one. Now, in this CSEC question, it says the diagram below, not drawn to scale, shows a circle with center O. The points A, B, C, and M are on the circumference. The straight line CN is a tangent to the circle at the point C and is perpendicular to BN. We want to find, given a reason for our answer, initially A, B, C. Now, when I start these type of problems, I kind of like to scribble the theorems on the side so that I remember what I'm looking for. Okay, so we have the one double angle, kind of something like that. We have the one where we have the 90 degrees on the circumference for an angle in a semicircle. We have the bunny ears, where we know, say, if we see it like that, the angles are going to be equal. We have the tangent and the radius. Okay. Am I missing out any guys? Fill me in. Which one am I missing out? Which one am I missing here? I know there should be about 7. So which one am I? Which one? Look at those sketches. Which one am I missing? All right. Yes. Christina, alternate segment. Good. So we know, say, angle between a chord and a tangent is equal to the angle in the alternate segment. And I kind of like to color them. Well, that if you're in the exam, I have different colors, but generally you don't have that. So those two are the same. Those two are the same. This one is 90 degrees. And if this one is X, then down here, so it's 2X. Which one am I missing, guys? That's 5. That's 5. Cyclic quadrilaterals. Well, and for Christina, yeah, cyclic quadrilaterals. That's another one. So opposite angles in a cyclic quadrilateral sum to 180 degrees. So here, again, let me just color code. Let's say this was the green one. This was the yellow one. We're saying that the green and the angle in green and the angle in yellow is going to be equal to 180 degrees. Okay. 1, 2, 3, 4, 5, 6. Still missing one. Angle to the circumference in a semicircle is 90 degrees. Yeah, that was this one up here. That was that one. Yeah, two tangents are the same on the outside of the circle. In other words, if I have a circle and the two tangents, they are gonna be the same length. Right? So this is the same as this. So I kind of like to just have that there just as a reference, just as something to go by, just to help me as I go along. So that when I'm ready to look for the theorems now, I can look back on these and say, oh yeah, it look like that. So that's what I'm looking for. So let's do that. So first we want to find ABC. And especially if you're struggling with circuit theorems, this is a good place to start. Eventually you will remember them and you will know what to look for when you're doing it. Yeah. All right, so let's start. ABC. So what would ABC be? First, let's identify ABC. ABC is right here. What would that angle be equal to? And what theorem would help us? All right, Christina says ABC is 32. You can turn on your mic and explain how you know that, which theorem help you? How you figure that out?
All right, because of angles inside a semicircle. So you know that the angle at C would be 90. So if you add up 90 and 58 and subtract it from 180, you get 32.
Very good, yes. So now, if we look at that, you see that, guys? This is a angle in a semicircle because AB is a diameter. Actually, let me use something that's a little thinner. Oops. Yeah, AB is a diameter. So if you're using that information, then you know that that angle is 90, that one is 58, so we can use the triangle. All right, good. Yeah, thanks for that. So what's our reason now? We know that since we don't have a lot of space working here, should I probably put more space? Since angles in a semicircle, or rather, let me say, since the angle formed in a semicircle is 90 degrees, then the angle ACB is 90 degrees, which means that ABC is equal to 180 minus 90 and 58. And as we know, that is 32 degrees. So ABC is 32 degrees. So see, if you just wrote this, see if you just write this alone, you're going to get only 1 mark. You probably not even get the mark. You probably not have mark. You have to write out your reasons why. All right, good. So I can fill that in and say this is 32 degrees. All right, let me copy my diagram and continue down. So in the next question, number 2, says we want to find angle CMB. And that one is also 2 marks. So angle CMB. Let me make this bigger. CMB. Where is CMB? First of all, put it in green. CMB is right here. Okay. Now, what theorem can help us to find CMB? Let me look at all of the things that CMB are involved with first. Right? If I look at CMB, I notice that it's a part of it's a part of, let me highlight it, CMB. It's a part of a quadrilateral, like what Serena here is saying. More specifically, it is a cyclic quadrilateral because all the points of the quadrilateral touch the circle. Right? Anybody else seen that? Anybody else seen that here? This is a cyclic quadrilateral. I have to see it, you know. Right, good. So since that's a cyclic quadrilateral, then what do we know about cyclic quadrilaterals? Seen in the chat here, Ninja is saying cyclic quadrilaterals and angles opposite each other are supplementary. Yeah, basically. So opposite angles in a cyclic quadrilateral are supplementary. They add up to 180. So that means 58 degrees plus CMB is going to be equal to 180 degrees. Therefore, CMB is equal to 180 minus 58 degrees. And that is equal to 122 degrees. Okay? So CMB is 122 degrees. Why? Opposite angles in a cyclic quadrilateral are supplementary. All right. So that's how we figured that one out. So we look for the cycle, we look at what CMB is a part of, and we use that to help us to solve. Yeah. So remember, we just keep on looking for the theorems. We just want to get a little, just an idea that is that one. We just want to see it. And what can help is if you trace that one, that really helps as well. Anybody is not sure how we found that? Everybody is clear on that one? You see where the 58 degrees was opposite to CMB? Let me know if you're good to go. Good, all right. Tamaya, good? Stacy, good? No. All right, cool. Let's go to NCM. Again, I already have the diagram here, so I don't have to carry down anything. So NCM, what is that? NCM. Let me rub out this part. NCM, put it in yellow. So NCM is the angle that's right here. And the angle that's right here. So what would NCM be equal to? Now, let's think about it. I see your answer. I'm going to adjust it a little. NCM. Let's look. Where is NCM? See NCM here? NCM is this. Okay. And do we know anything? Well, for one, we know that the angle here is a right angle. Okay. The angle CNM is a right angle. So that's one thing that helps us. And what else do we know? I think we just figured out that CMB was 122 degrees. That's in green. So if one way that we could do this is that if we know our angle here, then we could figure out angle C. And it's possible to know that angle because angles on a straight line add up sum to 180. Right? So because angles in a straight line sum to 180, then that means CMN would be equal to 180 minus 122 degrees. And I think we already know that that is 58 degrees. Yeah. So that means the angle that we want, NCM, okay, is going to be equal to 180 minus the 90 and the 58. Right? And what's 90 and 58? Well, we know that that's 148. So that's 180 minus 148, and that is 32 degrees. So NCM is equal to 32 degrees. Right? And how did we, and what helped us? Angles on a straight line sum to 180 degrees. Okay, so that's one thing that helped us to solve it. For the I'm seeing what you're saying about the alternate segment theorem for NCM, but then one of the things that I wanted to look at very carefully is where NCM is, right? So if you were to look at the chord that it is on, okay. So if you were to look at the chord, let's try and see if we could do that. So if we look at the chord it's on, that means we would have to be taking into consideration the parts that come from the chord. And here, what does this tell us? It would be telling us that some other angle would be equal to 32, but not necessarily this one up here. Sorry, not this one down here for the alternate segment. And so we have to be a little careful with our reasons that we have. So it would be 100. Sorry, it would be 32 degrees. NCM is 32 degrees. All right. Anybody has any questions? Everybody good so far? Good. It's clear. We can go to the next CSEC question. All right, great. Now, this one, PQ. You know what I'm going to do next time? I'm going to draw some questions outside of C-Sec too, you know. Because you have some really good questions with other ones. PQRS, R and S are 4 points on the circumference of the circle shown below. Angle QRS is 58 degrees. Using the geometrical properties of a circle to give reasons for each step of your answer, determine the measure of. First, we're starting with SPQ. No. If we look first, let's identify SPQ. SPQ is down here. Again, we're walking, it's like we're walking with our theorems. Look at SPQ. What is it a part of? What is it a part of? What is it a part of? And you see the thing about these two, you know, like another way that you can do it, you see, when you get the diagram, you can just try to start identifying different angles on it. Because sometimes you might find that that help you. By the time you finish, like you just freestyle it, then you will know, you will be able to put in the answers for each of them. That can help you to think more freely. But that's something that you could also do. 64. Where you get 64 from, Christian? Where you get that? Where you get that? I see you laughing, so you know that that's not it. Let's look at SPQ. What is it a part? It's a part of a couple things here. But if you notice, it's a part of this figure. And the reason we can look at it like that, the reason why we choose that one, that's the one where we know the angle for. So good, very good. Baby munchkin, I don't know what that is, but yeah, very good. So that would be cyclic quad, baby munchkin. So 58 degrees here. We know that opposite angles in a cyclic quad sum to 180 degrees. So what does that tell us? This tells us that angle SPQ is equal to 180 degrees minus 58 degrees, which would be, wait, we never did something like this a while ago. Because time before, oh, that was the same type of, okay, it's pretty cool. Well, I guess CXC like the number 58 for some reason. So 180 minus 58, that is 122 degrees. All right? So SPQ is 122 degrees. Why? Opposite angles in a cyclic quadrilateral are supplementary. So now we're getting brave. We're doing them even without the theorems that we draw beside us. But remember, if you have to draw them, you know, they're like the wheels on a tricycle. They help you to get by until you can ride the bicycle alone. All right, OQS. So let me copy this diagram. So just find out the SPQ is 122. All right, so now we want to find OQS, and this would be OQS right here. So talk to me now. OQS. What is angle OQS? What theorem do you see jumping out at you? Which one are you going to use? First, we know OQS. OQS is, put it in green, is right here. So how are you going to figure that one out? All right, I see you see that one. Yeah, angles at the center is twice the angle at the circumference. So how can that help us? Well, the angle at the center is 58. So the angle that would be twice or 2 times 58 would be down here. So that, let me zoom in a little. That angle would be what? 2 times 58. 250 is 100, 816. So that's 116 degrees. And then I see you guys saying isosceles in the chat. Why is it an you identify that this is an isosceles? Good. But why is it an isosceles? Just to make sure we know why and when it applies. Why is that an isosceles? Why is that an isosceles? Yeah, Z, that's right. Because the sides come from the center. Good. So both of these are radii. Okay, good. There are 2 radii. And that's why this forms an isosceles triangle. So that means this angle over here is going to be the same thing. So we are now armed with lots of info to help us, because we can say that which one was 116 again? SOQ, angle SOQ is equal to 2 times 58, which is 116 degrees. And why? Because the angle at the center That's the only thing with this. Yeah, it's only by writing out. But remember, you have to put your reason. It's super important. Angle at the center is twice the angle at the circumference. And then now we know that since triangle OQS forms an isosceles where OS is equal to OQ, then angle OQS, the angle that we want, is going to be equal to 180 minus 116 divided by 2. Because remember, say, the two angles are going to be equal. Now, 180 minus 116, that's 64 degrees. And 64 divided by 2, that is 32 degrees. So angle OQS is 32 degrees. All right? And the thing is, you don't have to write it exactly like me, but you just want to make sure you identify, you have clear reasons for why you do what you do. All right, so I don't think I'm going to get these names any other. Saish, you asking me to repeat which one of them. How we get which part of it? Write in the chat, tell me where you're talking. Okay, the 180 minus 116 divided by 2. That was kind of a little stretch, but essentially what we said was that because angles, these two angles are equal, then the sum of the angles, half of the sum of the angles would be one of them. That don't sound like what I want to say in my head. The angle right here is equal to the angle here. So when you take 180 from 116, you have 64 degrees left. Since both of the angles are equal, you could say that 2 times the angle we need, or we're trying to find what each of these angles are, is equal to 64. So one of the angles must be 64 divided by 2, which is 32 degrees. And we wanted OQS, which would be one of those angles. Huh? That makes sense what I'm saying? Okay, good. All right. Didn't start off 100 there, but I'm glad eventually you got what I was saying. All right. Now, with that in mind, let's go to our third CXC question. Okay. Third CXC question. And in this one, P, Q, R, and S. Oh, sorry, no. What am I looking at? The diagram below, not drawn to scale, shows a circle with the center O, EH, and EF are tangents to the circle. FOG and JOH are straight lines, and the measure of FEH is 44 degrees. And you want to calculate, giving reasons for your answer, the measure of EHF, well, starting with EHF. So we'll do the rest as we go. All right, now here you see this circle looks a little bit more complicated, but let's break it down step by step. So first we want to find angle EHF, which is right here. What theorem do you think can help you? What do you already know? And how are you going to use it? What theorem are you thinking? Let me hear what you say. What you say? I'm thinking. All right, no. I want you to look carefully at it. Let me ask you a question based on what you have here. Could we use the tangent, the theorem for the tangent and the radius? What do you guys think? Could we use that theorem where we say the tangent meets the radius at 90 degrees to find EHF? Would we? All right. Let me see what you guys say in the chat. So I'm seeing 2 answers so far saying yes, that's what you would use. What about the rest of you guys? Do you guys think that that's, let me see what you guys think. Look very carefully at that line HF, you know. Is it really a radius? That's what I wanted to think about. Is it a radius? Because that's what you're looking for. That's when the theorem works. When we're dealing with a radius, the angle between the tangent and the radius. So we have to look at the line. And when you look at the line, this is not a radius, so that wouldn't be the theorem. Right? But that's one of the nice things with these questions. You have to look out. Well, nice is a strong word, but that's one of the things with these. You have to kind of just look very carefully, especially when you have a lot of lines. Look at it good. Right? Think about the words in, so sometimes it's not necessarily just how it looks, even though the diagram sometimes drawn like that, you have to look at, think about what the theorem says and if it matches up exactly with what you have there. So because that is not a radius, we can't use that. But look at it, we have 2 tangents meeting an external point. This tangent here and this tangent here meeting, going to the point E. So if EH and EF are the same length, because that's what the theorem says, that means this is an isosceles triangle where the angle here is going to be equal to the angle down here. So each EHF and EFH are going to be equal, right? So EHF, well, let me write the reason first. So since the lengths of 2 tangents that meet at an, I feel like I'm putting in too much words here, external point are equal. You could have probably said it in less words, but yeah. That means EHF, or rather triangle EHF, forms an isosceles. Therefore, the angle that we want, EHF, is going to be equal to 180 minus 44 divided by 2. 180 minus 44, that is 136. Check me. From that, that's not it. And 136 divided by 2, it's not close to 140, it's not 70. So 68. 68 degrees. So angle EHF is 68 degrees. And we know that because of our theorem about the angle, the lengths of 2 tangents that meet at an external point. Okay. So guys, again, just be very careful with your chords and your radii. Now let's go to the next one, FGH. I don't think I have to copy this one. I think we can just use it. So FGH. Where is FGH? Put it in blue. FGH is right here. What is angle FGH going to be and why, most important? What are you guys thinking? What is that going to be? Let me hear your thoughts in the chat. First, let me trace over FGH. FGH. It's nice, forms a little thing here. What theorem you think you can use to help you with this one? What do you know and how can that help you? Let me zoom in. All right, no, let me take what you're thinking there, Ninja. Let's take what you're thinking there. So, and Christina said, I think it's the same 68, but we're not sure. Let's look at it. Let's look at what we know. What do we know about the angle down here? Do we know this angle? Yeah, we know that that angle is 68 degrees. So here's what I want you to focus on. Using what you know can help you. Right? So always look for what you know first. Look at which angles you know and where. So for you know that that angle is 68 degrees. Without doing anything else, I also know that this angle is 90 degrees. Can that help me? Could this angle help me here where FGH is 90 degrees because it's an angle in a semicircle? Not necessarily, because even though I know that this is, well, it still could, might be a little longer, still could, because if I were to figure out this angle, then I could find it. But you remember earlier I told you that the alternate segment is like it's save at the end of the day, because that's a theorem that we could also use here. Angles in the alternate segment are equal. And when you look at this figure, FGH forms a triangle and angle FGH is in the alternate segment. Therefore, FGH is going to be 68 degrees, right? So FGH is equal to 68 degrees. Why? Because the angle, I can write it easily, angles in the alternate segment is equal. Right? So that is one way that we could use. That is one way that we could use. So that's how we know that this one up here says 68 degrees. All right? Everybody following me so far? Everybody following me? Yeah? Good. All right. No, Christina, I like that you figured out that that was not the only way to do it. That's not the only way, no, because we could also use that same theorem with the right angle, because yes, as I say, this forms a right angle, down here says a right angle, so that means this must be 22, and then we can figure out what that angle would have been. So the point is, you can use a lot of different ways to figure out what you want to know in circle theorems. But all you have to do, just make sure you look out for the theorem. All right? So boom, let's write that. And I see you got the answer to Ninja. Very good, very, very good. Very good. So let me copy this and let's move onward. Now, the next one we want to find is angle JHE. Then JHE. So here we have a little diagram. That one, this one is 2 marks, 2. JHE, where is JHE? JHE, yeah, JHE. JHE would be all of this. Right? So you want to find angle JHE. What would JHE be equal to and why? Let me zoom in. What are you thinking? Look at the sides that make JHE and see if you can pick up something there. So again, you love trace, you know. And if you are like, if that's why I like even if you have highlighters, you can carry them into the exam. Nobody not going to kill it. Because you can see it a little better. So JHE. What you notice? What you notice? Yes, Ninja. Good. The angle here is 90 degrees because it is formed between the tangent, which is EH, and the radius, which is OH. Right? So JHE is 90 degrees. We can write that over here. Which is 90 degrees because the angle between the tangent and the radius is 90 degrees. Right? That would be. Would JHE be 44? No, it wouldn't be, you know. It wouldn't be. It wouldn't be. I wish you were here to tell me why you're thinking that so I could help. But for JHE, notice that JHE is all of this. And then this one is 68 degrees. So it couldn't be less than 68 degrees. I don't think yeah. All right, boom. Let's look at the last one now. JGH. So let me get the red one. JGH. Where is that? JGH. Well, boy, with all of what we just been through, this one we can see that one right away. JGH right here. Live and living. What is it? What is this angle? JGH. Yeah, that's right. That's right, Christina. 90 degrees. Because it's the, but I don't like that reason though. Make sure you don't write that at the exam. As in, you have to write out a full statement. Or why you're thinking that. Yeah. We can't work with that. So why is that so? Like, the reason is JGH is 90 degrees. Why? Because the angle formed in a semicircle is 90 degrees. As we realize here, JH is a semicircle. So if I were to trace the rest of it, this is a semicircle. This is a diameter, sorry. So it forms a semicircle. And that's why that angle would be 90. All right. All right, good. So I think, well, this is the last question where we're at that time. This is the last question we're going to look at. But you notice again, guys, as I said, if you are still struggling to remember the theorems, just remember, know what they are. And then on your exam paper, just scribble them to the side and then look for them whenever you're working. All right? That's one thing I wanted to remember. Two, look very carefully at the parts that you're working. So make sure you understand, you know exactly what the theorem is saying. So that sometimes you don't, in order for you not to confuse, like when to know it's a chord versus a tangent versus the radius and stuff like that. And then three, always put your answer. Always put your reason, sorry. Always put your reason. I think you guys did fine with putting the reason. Some reasons I never like. Some reasons were some one word reason. Not throwing any word to somebody. But yeah, I think it was generally all right. But just make sure that you have your reasons listed. And a way to prove what you're saying. All right. Yes, like yours. Is you always throwing word fact. Like yours. All right, guys. So we'll stop here for today. I think I'm gonna look back on the poll and see the other ones that you guys mentioned. What if we do have another session? It's probably gonna be same time Wednesday at 7. So you can just look out on our community tab to get updates for that one, when and where and how. And if you're not subscribed already, make sure that you subscribe so that you can be updated with anything that you need to know. All right. So it was good. Linear programming, I was just talking with my class about that on Monday. I don't want to touch any topics that are kind of, they might come and then they don't come. I think linear programming is one of those topics. It's not every year you see it. It's like a on and off thing, every now and again. So I kind of want to wait until I see that list of topics from CXC before we choose like stuff like linear programming or those topics like direct variation or like distance speed time graph. Yeah, I don't want to choose that yet, but we'll see how it goes. All right. So all the best, everybody. As I said, remember to like and subscribe, and if anything, I might see you next week. We'll see how it go. Take care. Let's start this thing again. Oh.